Hi everyone, this is Lab 5 for Physics 2212. The purpose of this experiment was to collect observational data from a magnet falling through a conductive tube of aluminum foil. We will then model the tube and magnet interaction computationally. We will compare the computational predictions with the observed data. And then here's our main results. We had the experimental time was 1.456 seconds, and then the computational predicted time was 1.97 seconds. For our fundamental principles, we have Faraday's law and Lenz's law, which explain how nature abhors a change in flux by creating an induced current to counteract the change, and the induced EMF is directly proportional to the rate of change of magnetic flux. The Biot-Savart law allows for the calculation of magnetic field, and we will use this specific manipulation of the equation for this experiment. Newton's second law states that force is equal to mass times acceleration, and this will be used to calculate the gravitational force acting on the magnet. Since we are treating our tube as multiple stacked rings for the computational model, we will use this specific equation of magnetic force to determine the magnetic force of a ring acting on the magnet. Lastly, here's how we will calculate the time derivative of magnetic flux in the computational model. As for the assumptions, we assume our Bauer magnet can be treated as a magnetic dipole. We will also assume that air resistance is negligible, so the only forces acting on the magnet are gravitational and magnetic forces. The experimental model, we have the system is aluminum foil and magnet, and the surroundings are everything else. The initial conditions are that the magnet has not yet been dropped, so there's zero velocity, and there is no magnetic force yet acting on the magnet. Then as for our procedure, we first assign the north pole to the bar magnet using the magnetometer app. We then drop the magnet into the aluminum foil tube, and we record how long it took for the magnet to enter and exit. We repeat this process 5 times and calculated the average to be 1.456 seconds, and we found that the magnet falls slower in the tube than in free space due to upward magnetic force from the induced current. And then, as you can see, we have the magnetic dipole and massive magnet listed on the screen, as well as the radius of the tube, the width of the tube, and the length of the tube. Here's the computational model that was used. Here we first defined our constants we will use. Here we define the mass of our magnet and the magnetic dipole moment. And then here we have our dimensions of our aluminum foil tube. This right here is a function to calculate the magnetic field. And then here is a function to calculate the magnetic flux. And this is the equation that we typed into our code. In this segment of code, we determined the motion prediction and visualization for the magnet as it moves through the tube. We treated the tube as a stack of n rings, and we calculated the magnetic force on the magnet due to each ring. Therefore, the total magnetic force was equal to the sum of the magnetic forces acting on the magnet from each ring. We then determined F net by summing the gravitational force and the magnetic force, and we use this value to calculate the magnet's velocity and updated position as we continue to pass through the loop. This is what the output of our code looked like. From the computational model, it was determined that the magnet spent 1.97 seconds in the tube. As for the velocity versus time curve, it is clear, based off the shape of the plot, that the magnetic and gravitational forces were unbalanced in the beginning and end of the motion of the magnet, which resulted in a change in velocity. However, in the middle, the forces were balanced with one another, resulting in a non-changing constant velocity as the magnet moved through the tube. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. When viewed from above, the red corresponds to counterclockwise induced current, and the blue corresponds to clockwise induced current. This was determined via Lenz's law. The experimental model revealed that the magnet spent 1.456 seconds in the tube, while the computational model predicted the time to be 1.97 seconds. The resulting percent difference between these two values is 30%. To make the computational model more accurate, the tube could be divided up into more rings. We could also repeat more trials and try to recalculate the magnetic dipole moment to obtain a more accurate value. As for sources of error, the biggest source of error is most likely attributed to an incorrect dipole moment obtained from experiment 3, which resulted in inaccuracies in the computational model. As for other possible errors, the magnet may not have been dropped straight, causing it to hit the walls of the tube, and there also could have been human timing errors. For the first what-if question, if the resistivity of the conductor was reduced to as close as possible to zero, this would result in a larger induced current, which would then cause a stronger magnetic field, which would then cause a greater opposing magnetic force. The end result would be that the magnet would fall slower through the tube. As for the second what-if question, the holes would affect the induced current, leading to an overall decrease. Decreasing current would cause decreasing magnetic force, and the end result would be that the magnet would fall faster through the tube. Overall, there were discrepancies between the experimental and computational models, but regardless, in both models, the magnet fell slower through the aluminum foil tube than it would in free space, and this is due to Faraday's law. This lab served as a real-world model of Faraday's law, which helped provide a better understanding on the principle. Thank you so much for watching.